Okay, we should start. Sorry, it took me a couple of minutes to get Zoom to cooperate. So what's up today? So we need to go through the final evaluation so that I can write the report. I'll try to keep it brief. Then we will be wrapping up the generalized context model. And then we have the last part in which we can discuss. Yes? Did I not? Then I will post the slides. Just let me stop sharing. Good. And then we will close the more lecturing part of the course with a bit of inverse classroom on the prototype and rules as they were in the course notes. Questions on this? Good. Okay, so final evaluation. I think it's put Linus down here. Yes. And is away somewhere else. Okay, so generally, thanks to all of you who filled in the questionnaire. The outcomes are generally very positive, so thanks for that. I try to extract a few points, if I can make it work, where there's generally was expressed satisfaction to the fact that your voice gets listened, which is crucial, especially in complex and technical topics. There were several people mentioning the course notes. I might have primed you by asking you several times if the course notes were working, but it's fun to prepare them. It takes a lot of time. I'm also interested in hearing how they work. And there were general appreciation for the idea of portfolio assignments, which both have a structure that's clear and you can follow, but also allow you to sort of explore in different directions. So that's some of the things that I will mention as things that should not be changed. In terms of things that can be revised or rethought or at least discussed, there's the perennial theme of integration with decision making, where some people were feeling that a lot of the Bayesian workflow ideas that were clarified in the first two lectures could have benefited you at the beginning of decision making. This is something that we're discussing forever and ever. It's not an easy things to solve, but we are at the very least trying to sort of integrate the contents in more explicit ways. I don't know if you have very specific comments on things that you would like to have been introduced to in different orders or better or something. Okay. Then there was somebody who was mentioning more practical examples, like the pizza example, and I found it because I was second guessing myself on the pizza example being very far out compared to cognitive examples, but it had the advantage of being very practical, and I realized that a lot of the cognitive tasks that we present here are, in a sense, small games. Like they are models of a social interaction, which represent well how we study these things in the lab, but don't necessarily describe very well real decisions in the world, for instance. And so I've been considering how to include more real life kind of models. One of the issues is that things get very complex very quickly. The other issue in my specific case is that most of the cognitive modeling that I do is in the context of either pure basic research or clinical research. Of course, clinical research could be one case of real life modeling, right, in which some cognitive tasks that are normally administered to patients can actually be used to do more thanks to cognitive models. Uh, that is something that I could very easily add, at the very least, to the course notes and bring in into the course. I've been talking a bit with colleagues out in the industry who use decision-making models. Ta-da! The course is over. Okay, the that have been using cognitive modeling out in the real world, trying to figure out which kind of examples could work. And I know that at the very least, there's some soccer decision-making stuff that has been done, but I'm less familiar with these things, and there's a lot of complexities that always come in. So it's it's less obvious to me how they could be worked out in a pedagogical framework, you know, uh, building up the skills. So one possibility would be to bring some guest lecture or have some recorded video of guest lecturers that would present these specific models. I'm not very optimistic about introducing these real world examples in the pedagogical flow, but I'm actually very open to suggestions. Yes? Yeah. Yes. Mm-hmm. 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 Yes. Other comments? Yes. Mm-hmm. Yeah. Yes. So the way I would paraphrase it is while basic simulations, let's say of distributions, right, feel quite intuitive, as soon as we start adding not only a complex model that generates the data, but also concrete details about an experimental setup, then things get hairy and it takes perhaps a bit more hand-holding, or not hand-holding, but a bit more scaffolding to uh, work through that part. Hmm. Yeah. So something like even like a work flow chart of the different steps in the simulation. Yeah. Yes. Yes. I think that's a good point. Yeah. Yes. Mm-hmm. Mm-hmm. Yes. So one of the things that so this was a point that came before, so we ended up having four assignments instead of five. But that's I wonder whether I can anticipate it a bit more so there's a bit more time. Yes. Mm-hmm. 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 Yeah. Yes. Week. Yes. Good. Then, while we're talking about portfolio assignments, I've been running through my head some different forms of assignments that could be used. I think that so one of the things that we keep discussing in the department meetings is like the balance between group work and individual work. And one way that I thought some individual work plus some uh, building up of confidence could work was with in-class individual assignment early on. As we introduce Stan, just saying, okay, now individually try to build up a little Stan program that does these and that. The downside, and the reason I haven't introduced it this year is because there's something funny with the content and the programming skills, and doing a step back and saying now actually we just do a stand thing on something that you already know well. It sort of feels like filling some space that makes introducing the other assignments even later. So that's one thing that I'm still a bit on the fence, but I've been considering. The second one is that one possibility for a less work intensive final assignment, but then I would need to readjust the others, is that actually something like, okay, pick a chapter in the course notes and actually detail what should be improved in terms of visualization, in terms of explanation, in terms of blah, uh, and provide a pull request to improve that. And since a lot of the chapters now have gone through a few revisions, actually one idea could be to have some additional models that are there only as notes and that you could play with. Uh, so these are some ideas on other changes to the assignments from the portfolio. Any comments on that? Yes? Mm-hmm. Yeah, and the ergonomics is very different because you have the blocks and yeah. Mm-hmm. Yeah. Mm-hmm. Yeah. Mm-hmm. Yeah. Cool. Yes. Any other comments? Yes. Mm-hmm. Yeah. Yes. And I think now I actually want to also rethink assignment four so that it's more constrained. And then there's a final pick a chapter and try to revise the notes, which could be uh, a final part that's not as demanding as building your own model. And cool. Let me see. Is there something else? Do you want extra challenges? Haha. Okay, so I will be wrapping up these stuff in the final evaluation and in the new workflow that we have. I don't need the student signature anymore, but I think there's not going to be anything different from what we wrote here. Good. So before we move into the generalized context model, do you have questions, things that you haven't understood on the GCM and things that are puzzling you? Okay, I'll take that as a no, but I made an overview, right? So we did the GCM because, well, it works well in the categorization. It's an interesting example of an exemplar-based model. It's theoretically principled and conceptually interesting, but and also it's a model that can be made to work properly. There are more advanced models that I've mentioned before. For instance, the alcove. That's a model that uses a neural network-like structure to not only have the memory of the exemplars evolving as we already implemented, but actually having the weights changing over time as the participants learn how to direct their attention. The problem with those models is that I haven't seen any persuasive parameter recovery, and I know that Josh had a master student a few years ago trying to get the alcove with parameter recovery in JAGs, and nothing worked. So that's the reason for which we try also to stick to some models that we can make work. They might not be capturing all the aspects we're interested in, but they are ways of building our understanding of what an exemplar model can do, right? And we know it works. There was a neat development, which I thought was cool, that the models as they're implemented out there, they have no learning of exemplars as the model goes through the actual experiment, but it can be made to work through some twists that we've done, right? So basically where we have initial random choices if we don't have enough in the category, and then we keep adding the exemplars in the memory. There was also something that I haven't focused too much on, but there is a neat implementation challenge that's in these model, what we need to do is we need agents to store the exemplar in their memory. And as, for instance, we repeat the same aliens 3 times, right? There is an increasing computational cost of keeping things in memory. The model is simple enough that that's just going to slow down your computer and nothing else. So that's not a big barrier, but it's interesting to actually try to see how could these be reduced in ways that are or aren't realistic, right? Because if I want to do something that's not realistic, I could simply be having an index of all possible pairs, pre-calculated distance, and be outside of Stan, right? I can just give it the metrics. And then I don't remember the full exemplars, but actually I only remember the indices of the single exemplars that I've seen. But that's not very realistic, right? Um, Also, as you probably already seen in the course notes, that once we understand how the GCM works, it's pretty easy to transform that into a prototype model by having the centroid be what is remembered in the memory and updated and not all the exemplars. Good. So we went through the implementation of the single agent model last time. And if you don't have further questions on that, I will actually just go into the multi-level version. So what we have is that there's a few parameters that we want to build in a hierarchical fashion. So we have the scaling parameter, C. Do you remember what C is? Yes. What, sorry? Control. I can't remember if it has a specific meaning because it's C, but it's the parameter that determines how similarity decays with distance, right? So if we have a low C, we have a linear relation. As distance increases, or as distance, yeah, increases, similarity decreases. Uh, if we have a high C, we have a very strong cutoff, so that as distance increases, there is a threshold after which nothing is considered similar, right? And then everything in between, which corresponds to the model of exponential decay that we already seen when we're talking memory many moons ago. The other parameter that we want to make hierarchical is the weights, which is how much attention we're paying to the different dimensions. And in these specific example that I've been building up in the lectures, we have right, a typical experiment from the field where you have 8 stimuli, which are defined along 2 dimension, height, and I think they call it position. Right, so we have weight 1 and weight 2. Right? So what we need to do now is to make these parameters as hierarchical parameters. And the scaling parameter is kind of easy because it's what we're used to, right? So what we have is a population level C, which is defined by a mean. What's the mean of the population? And now here, yes. And the sigma, which is the standard deviation of the population. And just to refresh you, the standard deviation of the population is basically saying, if we assume the mean to be the true value, and we use that to predict the C of an individual, what's the average error that we get? In other words, if we go and sample from the population, how are the individuals going to be distributed, right? So the mean is going to be the average there, and the standard deviation is going to be the sigma. How spread? If everybody is very similar, it's going to be a small one. If everybody is very dissimilar, it's going to be a big one. Under that C, we're going to have the C for participant 1, the C for participant 2, and so on and so forth. However, as we go to the weights, that becomes less clear, right? Because the two weights are not two parameters that we can independently estimate or determine, because the way that the model works is that weight 1 plus weight 2 has to sum up to 1. Attention is a finite resource. If I pay more attention to one feature, I'm paying less attention to the others. It's not necessarily the only possible implementation, right? But that's what the model has been developed to do. So how do we create a hierarchical structure for that kind of constrained parameter? Do you have any idea? There's something on the projector, but so what we do is we can use a Dirichlet distribution, which automatically sums up to 1. It's also called simplex. And we can build a hyperparameter, the population level, by saying that there's two parameters. Now I need to remember which are they. It's kappa and I didn't write it. But anyway, we're going to have two parameters. One is called kappa and the other is called something else, which I'll look up in the next slide. The something parameter. And the something parameter is going to tell us how attention is distributed on average across the population. So let's say we could have a flat distribution so that the two weights get the same attention. The two features get the same attention. Or we could get a distribution where the first parameter, the first weight gets the most attention and the second gets the least. The kappa parameter is what tells us how distributed, how broadly distributed are the participants compared to the population level. So we have that a very high kappa gives us all the individuals being very close to the population mean. A very low kappa gives us very different distributions across the single participants. And again, since I have a hard time understanding this stuff just in abstract or even looking at the equations, the way I understand them is to generate a simulation. And of course, the something parameter is called weights. It's basically the weights of the population. So we simulate a Dirichlet or Dirichlet, I don't know, I can never remember which pronunciation, as a function that takes the weights of the population, the kappa of the population, and the number of the agents. We have a parameter that tells us how many weights there are, which is just the length of the weights. So that is something that you can very easily adjust to the alien case. We have that the individual weight parameter is individual weights parameters are generated using a random sample from the Dirichlet, R Dirichlet, which takes as n how many times it has to sample the number of the agents, which is the agents parameter. And then as the second input parameter, weights multiplied by kappa. So that if kappa is high, the weights become very high, very concentrated, if you want. They're not going to vary that much. If the kappa is low, the weights become very low, very diluted, and they are going to vary a lot. And then we just do a table in which these things are saved. Right. We can see here in the simulation that on the left, we have a kappa of 100. And we see that from weights that are equal between the two sides, the variations of the individuals is relatively small. And as I was mentioning there, if we have a kappa of 1, we have a lot of variation. Basically, a single individual can have any sort of combination. Right? Good. Then what we do is we start building our multi-level stand code, where we have that in the data, we have the number of subjects, as usual, the number of trials, and the number of features. And then we have that given that all the participants are going through the same sequence of aliens, right, we have a vector in which the length is the number of trials, and we give the true responses that participants should give on a trial-by-trial basis. The next is the actual decisions that the participants have given. which is not a one-dimensional array anymore because each participant can give different answers to the very same stimuli. So it's a two-dimensional array that has as rows the number of trials and as columns the number of subjects. And then we have the array of observations. Yes? Yes. In the data that you have, they're not. Yeah, it's been randomized before running the experiment, but it's the same order for everybody. That makes the modeling simpler. Yes. But if you had the randomization that's different by participant, you would simply make the Cat1 two-dimensional array. And now we are arriving at the real observations, right? Where here I've taken kind of a shortcut and I have an array that has as rows the n of trials. And we know that there is one stimulus per each trial. That's identical across everybody else. So I can make the columns the n of features. So the one column per feature. So I can describe the aliens as a vector or the stimuli there as a vector. If we had the randomization, we could do two different solutions. One is a three-dimensional array. Stan doesn't care. It's fine. You just put three things. Another is to separate the stimuli, which would be by trial and by participant. And then in a separate array, you would define with an index the stimulus and its observations, right? Its features, not observations. Yes. It's a bit like what SQL does. I don't know if you covered SQL. Not anymore. Okay, that was one of the things that was in data science. But yes, in any case, it's just figuring out whether you want the full BRMS style 3D array or whether you actually split things to save memory. Yeah, cool. Then there, we have an initial bias for category 1/2 because in that implementation, people can be more biased towards choosing danger or not danger. And then we have two values per prior. One vector that has as many values as the features. So we have the initial value of the weight for each of the features. And then a second array that has two value for C, which are the priors for sigma and for the mean and for the standard deviation. And we put the variables for the priors there so we can actually rerun the model, changing the priors, but not having to recompile everything. So it's easier to manipulate. Yes, this part is what we discussed last time, which is about its transformed data, right? Which basically determines two different indices, one for the, let's go to the aliens that are dangerous, and one for the aliens that are not dangerous, so that they have each their own list of indices. Then we also transform the parameters because what we have is we have that the parameter C, for instance, is something that as its value increases, its difference from the previous value decreases, right? The higher the scaling is, above, I can't remember if this is 5 or something like that, right? It's minimal at every increase because it's already almost a threshold, a step function. So the algorithm already at the single agent, but even more in the multi-level version, will the Hamiltonian Monte Carlo will keep getting lost in the long tail, right? It will try 6, and 6 does almost as well as 5. So especially if it's coming with a bit of momentum, if you remember, right? It will keep going that direction, and it's almost as good as 6, and is going to keep 7, and then 7 is indistinguishable from before, and it can keep exploring in that direction without really changing our ability to explain the data, right? So one way of avoiding that kind of behavior is to use a bounded transformation of the parameter. So what we do here is we take something that cannot go above 0, and we discussed that last time. So I'm going a bit fast, but let me know if you need more details. So we want something that has 2 bounds, one below because the C cannot go below 0. It just doesn't make sense. And one above because above a certain level, the C is not really giving us anything. A parameter that's bound on 2 sides is a parameter that's been logit transformed, right? It's in log odds. And while we usually see the logit transformed parameters to be between 0 and 1, there's nothing that stops us from saying times n, right? So that the bounded parameter between 0 and 1 becomes bounded between 0 and n. So that's something. So in the BRMS, if you've played with that, the BRMS package doesn't even have a logit and inverse logit function. It has a scaled inverse logit and a scale logit function where you can give it what the boundaries are. And basically what it does is implements versions of these times n. So what we want to define is the parameter C in a way that it's bound by these transformation. And there what we see is the C is given by the inverse logit of a C on the logit scale multiplied by 2. We could do 5. That was just a way of speeding up the computation a lot. Can't remember. I think in the course notes, I updated it to 5 just so it explores the full space. The parameter up there, W, is called alpha and it corresponds to kappa times weight. Why are we doing that? Well, if you remember when we went and simulated the Dirichlet, what it was doing is it was saying that the n of the agents was how many times it would have sampled from the Dirichlet distribution. And then there was something called weight times kappa, which was the second parameter, the concentration from which the weights were sampled, right? And so we are pre-calculating this weight times kappa so that it doesn't need to calculate it every time that it needs to sample for an agent. And that's the first one there. The next step is exactly the same that we have done before to calculate the distance and then similarity between the exemplar that we have seen now and all the exemplars that we've stored in memory. The only difference is that now, instead of having an array which is as long as the number of trials called RR, it's the rate at which we pick category 1. We have a 2-dimensional array with columns by participant, and we loop then not just through the trails, but through the participants and within each participant through the trials. And yes, this is really the boring stuff of saying we take E. So we take first for each trial the current exemplar, And then we loop through all the previous exemplars, calculate the distance, calculate the similarity, and then we average across the similarities to each of the two categories. We normalize by doing the similarity to category one divided the sum of the two similarities, and we get the probability of picking category one. And then given that sometimes it goes to 0 or 1, and that's problematic, we sort of bound it at 0.999 and 0.0001. Then we go to the model. We have priors, right? We have a prior for the kappa, the concentration. And here I put exponential. So it starts very close to 0. And now I can't remember what's the exponential of 0.1, but it grows, but not too much. I don't expect participants to be very similar to each other. And then there's prior for the W, so the weights of the population, which again is a Dirichlet because it's what generates values that are combined to 1. And I feed the prior values that I put in the data. And again, they look just normal priors. Usually you would then put a 1 and 1 or 0.5 and 0.5, so anything that's at the same level. Then we have the priors for the population level of scaling. So one prior for mean and one prior for standard deviation, which are sampled from the values that we feed to the data. And the prior for the standard deviation is normal truncated that we discussed before. So we want the standard deviation not to go below 1. And then I gave it something that seemed to work when I was doing the prior visualization, which was a standard deviation of 1. And we have, as before, that we subtract from the normal distribution with a mean of 0 and the standard deviation of 1, the log cumulative complementary cumulative density function, which basically truncates it at the value that we specify here. Then we simply loop through the participants and we say that their individual weights are sampled from the alpha that we've seen before, right? The weights times kappa. And then we loop through trials and we say that the decision for that trial for that participant is generated through a Bernoulli distribution with a rate of R that we calculated in the transform parameters. And then we can look at whether it recovers some of the data. I put in red the true parameter value. So for instance, there we have weight at the level of the population that for feature 1 is 0.8 and a weight for the second dimension that's 0.2. We have a kappa that was, I can remember, something like 0.8, so 8 or something like that. We have a logit of C that was at minus 1.7 and an SD that was a minus 0.8. And then we look at the distribution of the parameters. So how does this look to you? Yes. Mm-hmm. Mm-hmm. Okay, yes. So you didn't fall into my trap. Great. So if you look at the first two weights, which was a trap that I unconsciously generated for myself as well when I was generating the plots the first time. When I looked at those plots, it seems like, ooh, like for weight one, the posterior is going towards the left. For weight two, it's going towards the right. And now that I don't look at the x-axis, ooh, maybe the posterior is just not moving. It's just very centered, right? But then, and that simply happened because the ggplot automatically cuts in order to show you just the relevant region. But when you actually look at the uh, scale is not overlapping between the two, right? So the two estimates are not confounded. Yes, they are pulled a bit towards the center, but they're actually quite spot on. So well done. When we look at the kappa, again, we have another kind of dilemma there because what we see is that the kappa is saying that the true value has the highest possible probability, right? It's really captured by the peak. But there is a lot of uncertainty on the side, right? And well, when we're talking log odds, who understands anything, right? So how would you, so these could seem good enough, right? Once we think a bit and say, well, yeah, there's a lot of uncertainty, but it should be good enough. What would be your next step to make sure that it is good enough? Right. So if we think about a concrete application case, so for instance, we might want to know whether our participants, yes? Mm-hmm. Yes. Okay. Yes. So you're right. We're skipping a few steps that are actually, I can't remember if I uploaded the new version of the course notes, but there should be in the course notes, if not already now, later. Um, but the once you look at the posterior predictive checks and the like, you still are going to be a bit in doubt as to whether it is good enough, right? So if we think about an application, my usual kind of experiment would be to say, well, I actually put some structure in the data so that participants should be able to correctly allocate the weights to the 2 dimension or to the 5 dimensions, or I'm interested in whether dyads in your case are better able to allocate the right weight given the data. And so what I want the model to be able to do is to discriminate between different underlying values for the weights primarily, right? I don't have any strong hypothesis about C, but I might also have hypothesis about C. I generally don't. So what I would do is to actually do the full scale parameter recovery, right? We want to see whether the model can recover nicely different levels of weights and the rest. In a multi-level model, there is a shortcut, which is now we're looking at the population, but we could also look at the individuals. And so what we can see here, right, is the true C in the original scale or in the logit scale. It seems to be nicely recovered across individuals. I haven't put any statistics, but they line up nicely along the diagonal. When we look at weights, there seems to be something, but it's harder, right, to make any strong inference there. Of course, what I could do is I could put a geom smooth and see that it flattens out the closer it is to the extremes. But it's hard to see whether it's really good. So there's often no alternative to actually go full parameter recovery. Right? And there we are looking at different population means, which are easier to recover than the individual parameter estimates. We see, I can remember 1, 2, 3, 4, 5 different possible true underlying values. I didn't go above 0.5 because, yes, exactly, because, and also the two weights are 1 minus W2 is 1 minus W1. So as long as we can recover that range, we should be home. And you can see in red the true diagonal that they should follow, and in blue the actual diagonal that they follow, and it seems pretty good. And then we can do the same for the scaled logit and for the kappa. The kappa is actually the most crappy of those. And with that, we see that the model is working, and we take a break, 10 minutes break. So we should now start. So, oh, no, nothing so. Before we ran the full parameter recovery, we saw that certain parameters are more easily recovered than others, and therefore we often have, well, not therefore, but this is something that we often have as a trade-off in our modeling. We cannot always recover everything equally well. So we should really focus on the parameters that we are interested in. And you can go away. Yes. So take-home message from this part is that model subcategorization have multiple dimensions that can are interesting to explore, features, attention, representations, and depending on our research question, we might be interested in exploring differences in attention versus, for instance, differences in representation. So let's imagine, before we actually discuss it, that we are interested in how participants represent in their memory the aliens. Do you have any idea or suggestion on how we could go exploring that? Right? We're not interested in whether they allocate attention differently, but we are interested in, are there differences in how propense these participants are in remember, say, exemplars versus prototypes? Yes. Yep. Mm-hmm. So this is a traditional way of thinking about that in experimental terms, right? So we want to see where the models are making a difference in the behavior. And here's where simulation could help us, right? We could simulate from the two models and discover, for instance, that if these are the two categories, right? There is no clear centroid, but there's clusters. Then an participant using an exemplar model should perform better than a participant using a prototype model, right? A complementary way of doing that is actually to implement the two models, feed them to the participant data, and see which fits the data better, right? And the good thing of knowing both experiment design and cognitive modeling is that you can do both, so it becomes very clear. Because sometimes from an experiment that's not been optimized, you cannot do that from the cognitive models only. But on the other hand, the good thing about knowing cognitive modeling is that you can take real world data and actually start hacking at them with the cognitive models even before you rerun a new experiment, right? Good. A second point that I wanted to make out of this is that it takes a while to develop and validate a model. So while in especially stuff you might have done in methods 1 and methods 2, and to a certain extent method 3, you can just throw models at the problem. It's actually a really good idea to develop the model by spending a lot of time sort of thinking it through, running simulations, understanding the model even before you run your Stan stuff. Then a third point was that this was a very different model from everything we've done before, but the Bayesian workflow just works, right? We need to do a bit more structure of the simulation, which is quite important, but the general Bayesian workflow works very nicely. And then there was the fact that you will also see as you simulate your data that the experimental setup matters. So sometimes we have models that maybe have been developed in the literature and would work wonderfully exactly in the examples that have been provided in the literature. But as you apply them to your experimental setup, that might be slightly different, then a lot of things can go wrong. What happened in our case was that when we took the way that the model was implemented in the original literature on the GCM, first of all, it was crap at describing early phases of the game because our participants do not get trained. So even just the simulation told us that things were qualitatively different. But also, as we were trying to recover the parameters, and there have been other studies that have successfully recovered the parameters, we realized that having binary features was an issue for the model, and we had to tweak the priors and to tweak the way that the memory update worked, and so on and so forth. So that as you change the setup, even a model that's perfectly well validated in the literature needs to be assessed again. Okay, now we have I have some notes there that I'm not gonna open, but we have the more inverse classroom, unless you have specific questions on the GCM and or the assignment. Where I want us to briefly discuss how the prototype model and the rule model works. Right. So first of all, do you have remaining questions on the GCM? But that works. Okay, cool. As we move from exemplars to prototype, and really in the conceptual development of the field, prototypes came first, but it's easier to generate a model of prototypes once we went through GCM, right? What is the crucial change from the exemplar model? Yes? Yes? What's the change in memory? Yes. Okay. Yeah. And in the simple versions that we're working with, there's only one prototype, right? So given that we only store one prototype, what happens and as we meet a new alien? Because before we could just stuff it in memory, right? But now we meet a new alien. Let's say it's of the dangerous type and it's here. Yes? Yes? Okay, yes. This is a good point, and I think that it brings us matters of uncertainty in. Sabrina, did you have a suggestion in? Okay, so basically what we have is up now we freeze time, right? We've seen a certain amount of aliens, and we have these two prototypes, right? We forgot everything about the exemplars. Now we see a new alien, right? And we calculate the distance. And in this case, the distance seems to be much higher from category two than it is from category one, right? So and actually at least before we did the Manhattan distance, so that's going to be like this. Now it's very clearly bigger from category two than from category one. So it's going to guess category one. And it's gonna uh, guess right and got told that, yes, this was a dangerous alien. However, right, this dangerous alien is not very well captured by the centroid, right? We don't expect the exemplars to be captured very well by the centroids, but still it's telling us that there's something interesting in that direction, right? That some of these features should be, I don't know, the wavy hat should be more nicely captured by the centroid. So what do we do there? Yes? No. Now it's, but at least as we know, this is dangerous, right? Yeah, right. Yes. So we want to adjust the centroid, the prototype, according to the new exemplar that we've met. How do we adjust it? Right. The way I've done it here is basically I took dimension one and I made a mean between the two, right? And I took dimension two and I made a mean between the two and I put it there. But clearly, right, that would mean if we borrow the learning rate metaphor from reinforcement learning, that means somebody who sort of has a very high learning rate and it's moving around all the time, right? Which is not necessarily what we want to see. Yes. Mm-hmm. Yes, we want to add a weight. And what does the weight depend from? Mm-hmm. Oh, yeah. So you're saying if there is a high predictive error, if you want, in predicting the exemplar from the centroid, then you might move more than if it's very close. That's one dimension. Now it's Yes. Okay, so basically what we have is that we should consider not only the distance, but also how certain our prototype is, right? How confident we are in the prototype. And we should consider how certain we are in our observation. That is, whether we think there is a high or a low measurement error, which is not very different from implementing a learning rate. In order to do this, what we want to do is we want to use a Kalman, or we want to use an updating system that takes into account these two dimensions, and that's most commonly the Kalman filter. The details of that are in the course notes. Have you had a look at them? That's not a problem. It's there, so you can look at it as much as you want. But basically what it does is it says that as the basic version of the Kalman filter, as we observe more and more exemplars, our uncertainty around the around the centroid decreases, right? We become more and more confident that this is a centroid that is based on a lot of observations, so it must be good for something. So relatively to the new alien, we're going to move less and less over time. And we have a measure of observational error along the two dimensions, which roughly corresponds to the attentional weight in the exemplars, meaning that the more observational error there is, the lower the weight, the less it's going to matter. The smaller the observational error in that dimension, the more it's going to matter, meaning that a small change in that dimension makes a bigger difference, right? So it's conceptually at least very equivalent to the attentional weights, right? I'm not going to go through the mathematical details now. If you want, I can make a small cap with slides at a later point next week, but I think we're going to work on assignments. Let me see my notes a second. I had a couple of points on that. Yes. So imagine that you have these model playing the version of the alien game that you played, right? Which was characterized by the underlying prototype of a dangerous alien changing over time, right? What happens here? Is this model going to fare in any decent way? Yes? Yes. And over time, it's going to struggle more and more at getting to the right place because it's getting slower and slower at moving, right? And so this is, again, a model that has been developed in a case in which you've already seen all the training exemplar and you're sort of fixed, right? The Kalman filter in itself actually yields itself to be developed in this direction. There's something called the noise process, which basically says on top of that updating mechanism, at the beginning of each what's it called, of each trial, we're going to make a prediction about where we're going to find our dangerous aliens, right? Let's say, now I need more colors, but I don't have them. But let's say this area, right? And given that this new alien is here, and even with all its uncertainty, it doesn't overlap with that, right? We're gonna decrease the confidence of the model, right? We're gonna say we're actually gonna include this distance between the two distributions as a measure of how much we should update. And that creates a model that keeps on moving around. Does that make sense? And again, this is stuff that is not really in the literature, but as you learn how to move on these very basic mathematical models, then you can actually very easily import different ideas into the model that you want to do. Right? And so I made a plot there. I want to make a GIF, but I didn't have the time, where you can actually see how, starting from the center, the prototype of the two categories moves with any new exemplar until it reaches a good point, right? Good. Do you have questions on the prototype model? Yes? Yes? Mm-hmm. Yeah. It's a trade-off. Yes. So the question is, let's say that we get high predictive errors, therefore we keep moving the centroid. Does this mean that our centroid, our prototypes, become more general, or is it actually losing information from the past? And it's a trade-off between how much uncertainty you're getting, in a sense, depending on how you set up your Kalman gain, like the update system. You might have that your uncertainty just keeps growing bigger, which is a form of generalization, but it's generally very useless for producing predictions, right? Unless it is a very diffuse prototype. Uh, or you simply actually lose information, right? Because now you're meeting a bunch of agents here, aliens here, you increase your confidence, but then the rules shift. You first decrease your confidence, but then as you meet more aliens in this area, you start losing information about the past because it doesn't fit anymore, right? Does that make sense? Yeah. And you can actually measure the confidence on a trial by trial level and see whether it fits with when the rule changes, right? Because that would be a good measure of how the model is behaving. Yes? Yes? Mm-hmm. Oh yeah. So yes, absolute sense. So the question is, now we chose a binary case, which is easy to model. Uh, and it's also defined in a dichotomic, either A or non-A. But the way that we move in the world is that we have a bunch of categories, right? And so these kind of models, the way we discuss them, they assume that there is an n amount of categories, which is predefined. But as long as you have that, then the model works, right? It becomes computationally more heavy, but you're simply saying, I have a category here, 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 I have a category here. I meet a new alien or animal, and then I look at the distance between all of these, right? And then I say, okay, this is the shortest. So if we're in a deterministic system, I'm going to attribute it to this category. If I'm in a probabilistic system, I'm going to make some sort of normalization given everything else. And then accordingly pick the probability, right? So the model doesn't care whether it's 2 or 3 or 4 or 5 or 1,000. It just looks at which one is closest. No, no, exactly. Then the problem is that we often don't know how many categories there are, right? And that's where you have the Chinese buffet problem, it's called in the literature, where you need live to identify how many clusters there are. And there, the prototype model sort of shows a lot of the limitations because actually you need to have a bit of memory of how the exemplars are distributed to say, oh, right, here there was a cluster, but now we're finding a few here. Maybe we should assume that there is a second cluster here and maybe define a new centroid, right? And that's a very tricky problem. There's one of your colleagues, Christopher Olsen, who's writing his dissertation on PhD dissertation on how do we actually infer how many clusters there are in Gaussian distributions. Yeah, cool. Other questions on the prototype? Yes, yes. Oh, so in the prototype, we actually assume that there is only one cluster. Yeah. And then we move around. So there are attempts, as I was saying, at inferring the number of clusters live, but the standard prototype says there is one cluster. Yeah. And that's where if you have a clustered set of categories, let's say birds, where you have flightless birds and you have flying birds, then the prototype should perform worse than the exemplar based because it cannot really capture these fact that there are more centroids. Yes. Uh, mhm. Yeah. Well, so basically what the prototype model is going to do is probably it's going to fail, right? It's going to say now we're seeing these ostrich that's very big, doesn't fly, I don't know, can be ridden by and therefore it's going to be some sort of mammalian type, right? Uh, so while the exemplar might identify that there's a bunch of flightless birds there, and therefore when it finds another one, will find that there is a cluster of things that associate very closely to that. Uh, and again, we are living in an ideal world where we already have pre-mapped features, right? If we also want to discover which features are relevant, that's, you know, what we would be doing is we would need to have a universe that already has all the possible features. And what we would have is that we would have a very high uncertainty in those dimensions that are not relevant because we're not able to learn anything, right? It's going to keep on changing. And a very high certainty in the dimensions that are relevant because those are going to be uh, the ones that we can learn something about and therefore reduce the uncertainty. We still need to have all the features already there in our idealized model. That's where if you take connectionism and some directions in deep learning, the ability to discover new features is something that is very cool compared to traditional cognitive models. On the other hand, we have a really hard time getting a handle in the internal mechanism. Uh, yes. Cool. So if we take the rule-based model, right? Does anybody want to try to explain how the rule-based model works? Yes. 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 Uh, well, as you prefer. Like, let's do it with the alien example. Yeah. Yes. So, for instance, we have color equal green. It could be danger, or color equal blue. It could be danger, or arms up. It can be danger, right? These are all possible rules, and then we can go one level more complex and say blue and dots danger, right? Okay, so the idea is that instead of acting on these continuous space of features, we are acting on these kind of deterministic rules, right? What do we do with these rules? Yes. Mm-hmm. Yes. Yes. And in our model, right, how do we assume that the agents learn the rules? Yes. But let's say that even with the 5 features, I can't remember how many thousand of possible rules there are, right? So it's implausible that an agent would have all the 5,120 rules that can be generated. So how do the agents go in evaluating the rules? But think about your experience. As you were going through the experiment, yes? Mm-hmm. Yeah. Yes. Yes, absolutely. So in principle, you could have a weight on each of the rules, right? Except what happens is that you arrive to weight 5,000, right? And I don't know about you, but I can't keep track of those, right? So we need a mechanism that allows us to replicate something that's closer to what you were doing during the experiment and take only a few of the rules into account at a time. Yes, yes, we have a memory, and let's say that we say that our working memory can contain 7 rules, right? So how do we pick those rules? Oh yeah, so we say that agent one has 7 spots for rules, and agent two has 7 spots for rules. How do we put something in those spots? Yes. Yes. Mm, yes. So what we do is we basically randomly sample, right? We might have some criterion. Let's say simple rules get sampled more likely, right? But we have these universe of rules, which in our uh, computer world we sort of predefine, and then they are simply sampled from that universe. We have 7 rules. We meet an alien that has very thick legs, and then we get told it's dangerous, and then we say, okay, given the rules that we have sampled, right, how should we update their likelihood, right? They started all the same, but now all the ones that, I don't know, didn't have thick legs get downgraded. Does that make sense? And how we downgrade them? Well, we can use a Bayesian update rule, right? We can say, given what we had before, how likely is this rule to predict the actual uh, category of the alien that we've seen? Uh, and then we adjust that with the current weight, which is the prior, and then we get a posterior out of that, right? At a certain point, we will have, let's say, this rule and this rule that are going to have a relatively high weight and the others that have a very low weight. Right? So what happens in your conversation is that you say, oh, but what if instead we had to look at not just the thick legs, but the thick legs and the color, right? If we have at least one of these two, then it's dangerous, right? Which means that you're sampling, you're discarding these very low likelihood rules and sampling new rules, right? So there is a threshold under which the rules are discarded and new ones are tried out. These are called Bayesian particle filters, where basically they assume that each of these rules is like a particle. And the more you engage with the word, you can see whether these particles are right. Right? Comes from particle physics, right? Where you have a bunch of possible candidates for the data that you're observing, and you want to observe a lot of these data in order to sort of prioritize or down prioritize different um, potential candidates that generate the data you're seeing. But we can borrow that for categorization and do exactly the same. Right? The resampling is usually done at random, but there's nothing that stops us from doing a targeted resampling. What does that mean? It means that, for instance, if both these two high probability rules have thick legs, we're going to go and look sample from the set of rules that contain legs, thick legs, right? Instead of randomly sampling from everything. Sometimes we're going to be sampling the same rules that we already have in. And that's actually considered a feature of the model, because then it means that these rule gets duplicated. And therefore, it's going to matter for more in the predictions of the model, meaning that unless we start encountering individuals that don't fit this rule anymore, we're going to get more and more confident in that rule working. Does that make sense? As a very last bonus question, why would these models be very tricky to fit in Stan? Which is why there is no working implementation in Stan yet in the course notes. Yes. Yeah. So the big issue is that the agent at start will have sampled 7 rules, or if we also want to estimate the working memory parameter, a variable number of rules, and will generate a behavior that is clearly underdetermined by the specific set of rules that they have, right? Many different combinations of rules in the memory will generate the same dangerous behavior. And given that there is a very large number of rules, for the stand model to identify the exact rules that the agents, or even a plausible distribution of sets of rules that the agents might have implemented, is just there's not enough information in the data. So I'm pretty sure I can get there, but I need to we would need to make some trick and assumptions on how to solve that initial problem, right? For instance, we could say, oh, initially all the agents by assumption only sample amongst the one feature rules, right? I'm sure that then problems come back after biting me, and there being many rules after that could be resampled, right? It's these actual sampling of the rules that it's a problem for Stan. But with that, we can conclude the more lecture part of the course. You've seen a bunch of different models, you've seen a bunch of different techniques, and the next 2 times we'll meet, we'll actually work on your assignment. Thanks.